Ionic bonding. Now, ionic bonding is basically a bonding between a metal and a non-metal. As you can see in this diagram, a metal sodium is reacting with a non-metal chlorine to form the salt sodium chloride. This is ionic bonding. Let's further understand what it means. Sodium chloride is the easiest, best known example of ionic bonding. There are a lot of other ionic compounds such as magnesium oxide, calcium fluoride, zinc bromide. Now they all contain a metal and a non-metal. Furthermore, non-metals such as chlorine combines with the metals such as sodium. Chlorine atom has stronger attraction for electrons than the sodium atom. And this is because the number of protons present in the nucleus of chlorine, which is 17, rather than sodium, which is 11. Now, one electron is transferred from the outermost shell of sodium, this one here, all the way to the outermost shell of chlorine atom here. An electron has negative charge. When something gains an electron, it becomes negative. So chlorine is converted to a chloride ion, which is negatively charged, as stated over here. Sodium is converted into a sodium ion. Before we move on, the simple and obvious observations that we can see is sodium had 3 shells in start to begin with, and it lost an electron. And as the outermost shell only had 1 electron, the shell disappeared as a whole. So the size of the positive ion is smaller than the parent atom itself. On the other hand, chloride ion actually increased a little bit in size because it has to readjust itself in order to accept the incoming electron. The chloride ion is a little bit larger in size than the chlorine atom. As we can see the positive and negative charges, we can work them out with proper mathematics. Let me show that. In case of sodium, it's actually neutral because there are 11 protons and 11 electrons. Just a second, my bad, 11 electrons. Now, every proton has a +1 charge, so the overall charge on protons is +11, and every electron has a -1 charge, so the overall charge on electrons is -11. Mathematically solving, this is 0, which means the sodium atom is neutral. All atoms are neutral because the number of protons are equal to the number of electrons, and they exist cancel out each other charges or balance them. So what we get are neutral atoms. However, the case of ions are slightly different. Let's talk about sodium ion. In case of sodium ion, the protons are still 11, and the electrons are 10, not 11 anymore. The outermost electron has been lost to chlorine. So it's actually +11, but -10 in charges. Solving it mathematically would give us the answer +1, which is the same amount of charge we are showing over here. In case of chloride ion, Cl negative, number of protons are 17, while the number of electrons as it accepted 1 from the outermost shell of sodium is 18. So solving it would be +17 -18, and the answer to it is -1, which is shown as the charge of chloride ion. So sodium ion and chloride ions actually have plus and minus charges because of the whole charges on their protons and electrons. These charged particles are known as ions. We can simply call them positive ions or negative ions. A positive ion is also called a cation, for example, Na positive. A negative ion is also called an anion, for example, Cl negative. Now, an ionic compound is formed when electrons are transferred from a metal to a non-metal. The metal forms the positive ion, the non-metal forms the negative ion, and ionic compounds have ionic bonding. And ionic bonding is a result of strong electrostatic force of attraction between positive and negative ions. As they are opposite charges, so they're going to attract each other. And as we know from our previous classes, the term we use is electrostatic force of attraction. oppositely charged particles attract each other with electrostatic force of attraction. A structure for a typical ionic compound is shown over here. The alternate arrangement of particles, positive and negative particles, in the lattice, in the crystal lattice, is shown over here. Ionic bond is often shown with the help of dot and cross diagrams. Now, dot and cross diagrams were shown above as well, although we have used all dots in these diagrams, but it's very easy to show either one of the electrons with a dot or a cross. For example, we can show the electrons of sodium with dots and that of chlorine with crosses. That is dot and cross diagram. Now, another example of dot and cross diagram is for magnesium oxide, the formula for which is MgO. Magnesium loses 2 electrons being the metal, and oxygen gains those 2 electrons being the non-metal. Magnesium is converted to Mg positive 2 ion after the loss of electrons, and that of oxygen after gain of electrons is O negative 2. And the purpose, the actual purpose, we go with this dot and cross diagram is to show the 2 different sets of electrons. And that doesn't matter for cation because it only uses 1 set of electrons. But for the anion who gains the electron, this is very important that if anion was initially drawn with the help of crosses, there must be a few dots. And actually the dots are equal to the number of electrons gained. As you can see, it has all crosses, but there are only 2 dots, this one over here and this one over here, because these are the electrons that do not originally belong to oxygen. They have been gained from magnesium, hence the ionic bonding, hence the formation of ions. Moving on, the significance of noble gas electronic configuration in ionic bonding. Now, something we need to understand is that after the loss or gain of electrons, for the first 20 elements in the periodic table, we say that they achieve the nearest noble gas configuration, either after the loss or after the gain of electrons. Now, if we consider metals, we're going to consider group 1, 2, and 3 of the periodic table. And they are going to lose respectively 1, 2, and 3 electrons, forming positive 1, positive 2, and positive 3 ions. If we discuss the nonmetals in groups 5, 6, and 7, they are going to respectively gain 3, 2, and 1 electrons. Group 5 elements will form a negative 3 ion, group 6 negative 2, and group 7 negative 1 ions. Let's show a few examples to understand that. Aluminum is present in group 3. It has 3 electrons in its outermost shell, as drawn over here, 2 here, 1 here. It loses those 3 electrons and forms an Al positive 3 ion. Those 3 electrons are added to nitrogen, which is present in group 5. It has 5 electrons in its outermost shell. After the addition of 3 electrons, it forms a nitride N negative 3 ion, nitride ion. And as we can see over here, aluminum nitride would form by the electrostatic force of attraction. Now, we need to compare these examples with the nearest noble gases in order to understand the importance we started off with. Sodium, after the loss of 1 electron, becomes an Na positive ion. And take a look at its electronic configuration. It's exactly similar to neon, the nearest noble gas in the periodic table. The term we use is isoelectronic. It means they have same number of electrons. Na positive and Ne have same number of electrons. If you look at the examples of Al positive 3 ion, it also has the configuration of neon, as well as nitride in negative 3 ion, which also has the configuration of neon. So actually they have the configuration of the nearest noble gas. Moving on, elements in group 1, 2, 6, and 7 always form ions that are isoelectronic with the nearest noble gas atom. For example, rubidium, which is in group 1, has 1 electron in its outer shell and will lose that electron to form a positive 1 ion, which has the same number of electrons as krypton, the nearest noble gas. Iodine is in group 7. It has 7 electrons in its outermost shell. It will gain 1 electron to form an ion of -1 charge. That -1 ion has the same number of electrons as the xenon atom because that's the nearest noble gas to iodine. However, there are a lot of common ions that don't have noble gas structures, and most of them are either transition elements, iron +2, iron +3, copper +2, zinc +2, silver positive, or the weak metals present at the bottom of non-metallic groups, such as lead +2 at the bottom of group 4. Now, not all the ions are something you're supposed to go with in this IGCSE course, so don't worry about them because they don't have a typical nearest noble gas structure. Moving on, other examples of ionic bonding. What if the number of electrons transferred from one point to another is different? We are supposed to take a few examples with 1 electron loss or 2 or 3. So lithium fluoride is another example, which forms from the loss of 1 electron from lithium, the Li positive ion, and the gain of that said electron in fluorine as F negative fluoride ion, hence forms lithium fluoride. It would have strong electrostatic force of attraction between the Li positive and the F negative ions. Next up is calcium chloride. Calcium chloride is slightly different. This example is specifically taken in order to make sure that you understand the part where the positive ion is going to lose 2 electrons, but the negative ion can only gain 1. In this case, the metal is calcium, which loses 2 electrons and forms a calcium +2 ion. And we have chlorine, which can gain 1 electron and can form Cl negative or chloride ion. But as calcium loses 2 electrons, in order to balance the whole thing up, there would be 2 chlorine atoms converted into 2 chloride ions respectively by the gain of 1 electron each. So that would give us the formula of the compound CaCl2, which pretty much explains the presence of 1 calcium atom with 2 chlorine ones. Once again, there would be strong electrostatic forces of attraction of ions because the +2 charge on the calcium would make it even a stronger candidate for electrostatic attractions. Formulae for ionic compounds. There are so many different ionic compounds that we might encounter, so it would be impossible to learn all formulae, but we are going to work that out with the help of the electronic configuration. So first things first, the need for equal numbers of pluses and minuses. Ions are formed when atoms, group of atoms lose or gain electrons. Now they carry an electrical charge, either positive or negative. Compounds are electrically neutral, so the ionic compound must be in the right number of each sort of electrons. Like we just explained that calcium has a loss of 2 electrons, however, chlorine has a loss of 1. So in order to balance both, we need 2 chloride ions so that the charges could be balanced. Hence, the formula becomes CaCl2. So that's how we are going to work it out. Cases where you can work out the charge on an ion. Any element in group 2 has 2 outer electrons, which it will lose to form a +2 ion. Any element in group 6 has 6 outer electrons, and it has the room to gain 2 more. This leads to a 2 negative ion. So it's pretty easy to form a compound with those. Just like we formed magnesium oxide, in which magnesium was actually converting to magnesium 2 ions by the loss of 2 electrons. and oxygen was being converted into oxide ion by the gain of 2 electrons, so they balance one another. Going through the groups in 1 to 7, group 1 loses 1 electron, charge positive 1, 2 loses 2, charge positive 2, 3 loses 3, charge positive 3, and these are the examples we recently discussed. Group 5 gains 3 electrons, negative 3 charge. Group 6 gains 2 electrons, negative 2 charge. Group 7 gains 1 electron, and it has negative 1 charge. So as we have just discussed, the examples of nitride, oxide, or bromide, or any halide ion for negative charges. Remember, all metal atoms form positive ions, and non-metals will tend to form negative ions in ionic bonding. Moving on, cases where the name tells you the charge. All metals form positive ions, just as I explained. Names such as lead-2 oxide or iron-3 chloride or copper-2 sulfate tell you directly about the charge on the metal. The numbers after the metal tells you the number of charges, so it's pretty easy to understand. You can easily understand it, but let me tell you, numbers written ahead of names are always written in Roman numerals, and you're not supposed to use actual numbers for the purpose. Ions that you should learn because you cannot always work them out. Zinc with Zn positive 2, silver, Ag positive, hydrogen, H positive, ammonium, NH4 positive. Negative ions, nitrate, NO3 negative, hydroxide, OH negative, carbonate, CO3 negative, and sulfate, SO4 negative. Might I add a couple of ions to this list? We might need to go with phosphate ions, which are actually PO4 negative 3, and hydrogen carbonate ions. These are pretty much similar to carbonate ions. The only difference is that they have a hydrogen attached to them, which also changes its overall charge. Hence, the formula comes out to be HCO3 negative. So there are some ions which we need to memorize because we cannot always work their charges out. These are actually known as the ones with more than one atom are known as polyatomic ions. The word poly means many, and as they have more than one atom in their structure, so they're considered polyatomic ions. We have one important key point over here. Ammonium chloride or NH4Cl is an example of ionic compound that does not contain a metal. There is ionic bonding between the ammonium NH4 positive and chloride Cl negative ions. This is, however, covalent bonding, which would be discussed by the covalent bonding of ammonium ions in the next chapter. Now, confusing endings. Don't confuse ions such as sulfate and sulfide. A name like copper-2 sulfide means that it contains copper and sulfur only. Any IDE suffix means that there is nothing complicated there, just simply two atoms combined, one of copper, one of sulfur in this specific case. Copper has +2, while sulfur has -2 charge. There is an exception to this one, and that is hydroxide. Hydroxide is the only only polyatomic ion which is ending in the suffix of IDE, but is made up of two atoms instead of one. Once you have the 8 ending, it means there is oxygen with probably other things, other nonmetals. It can be nitrogen, it can be carbon, it can be sulfur, it can be phosphorus. For example, sulfate contains sulfur and oxygen. There is 1 sulfur and 4 oxygen atoms. Nitrate contains 1 nitrogen and 3 oxygen atoms. And you need to memorize their charges as we discussed on the previous page. Reducing the formula for an ionic compound. Let's start with the example of sodium oxide. Sodium has the +1 charge and oxygen has -2 charge. To have equal number of positive and negative charges, we need to take 2 sodium ions. So it's pretty simple that we can take 2 sodium ions and 1 oxide ion, and the formula is Na2O. Moving on to the next example, example 2, barium nitrate. Barium is positive 2 ion, nitrate is NO3 negative. You need to remember this. To have equal number of positive and negative charges, we need 2 nitrate ions. So this would become barium. And as nitrate is a polyatomic ion, whenever we need to increase its number, we are always going to use brackets, parentheses to be specific, and then write 2 outside. This one's correct. As explained in this key point, BaNO32 is incorrect. That means it has 1 barium, 1 nitrogen, and 32 oxygen atoms. This is incorrect. While this formula tells us there is 1 barium, 2 nitrogen, and 6 oxygen atoms, which is correct. Moving on. To find the formula of iron 3 sulfate, iron will have +3 charge, as the name suggests. Sulfate are -2. Now, in case of this, you'll have to have equal number of positive and negative charges. 2 iron 3 ions for every 3 sulfate ions would give 6 positive and 6 negative in total. We also go with a separate method of doing this. Iron has +3 charge. I'm just re-explaining this method by writing it a little bit differently. We are supposed to move this charge right at the bottom of sulfate ions, but without the positive sign, and this charge right at the bottom of iron ions without the negative sign. So it would easily become iron 2. I mean 2 iron atoms, not in the sense of the valency, and like this. So we write 2 beneath iron and 3 beneath the sulfate. So we get our examples. But if you're writing these numbers, and if they can be simplified, simplify them with the lowest possible numbers. Let me explain myself. Calcium and chlorine would be calcium chloride. I think it's easy to work with. But calcium and oxygen will get Ca2O2. You're supposed to simplify that into CaO, calcium oxide, because Ca2O2 is not correct. Remember, they are same numbers and can be simplified into 1 each. And remember, we don't write 1. So moving on, giant ionic structures. Ionic compounds form crystals. They consist of lattices. Lattice is a microscopic structure, a 3-dimensional structure with positive and negative ions packed together in a very regular way. It's a regular array of particles, positive and negative ions, of course. They're held together by strong electrostatic force of attractions, as we previously saw the diagram, the lattice of sodium and chloride ions alternatively arranged. So a lattice fence is actually a lattice-like repeating regular structure, as I've explained earlier. This is the lattice for sodium chloride. Sodium are depicted with small gray balls, and chloride ions with big green balls. As I've stated earlier, that sodium ions are smaller in size as compared to chloride ions. So this is an open up view, an exploded view, so you can understand that they are given in a packed alternative arrangement. Instead, the actual structure is pretty much close to one another, leaving no space in between almost. So each sodium ion is surrounded by 6 chloride ions. It's more like a 3-dimensional structure. If the sodium ion is right in center, this one, let's consider this one. There is one chloride ion up top, one at the bottom, one in front, one at back, one at right, and one at left. So it is surrounded by 6 chloride ions. And in turn, every chloride ion is also surrounded by 6 sodium atoms. So the pattern repeats itself throughout the structure over a vast number of ions, over ions that are not even counted by millions or billions. Numbers are even bigger, or even very smaller of mass values. The structure of sodium chloride is described as a giant ionic lattice. We use the word giant and not in the sense of big, but rather to describe that the structure where there are no individual molecules. All the sodium ions in the structure attract all the chloride ions. We cannot pick out sodium chloride molecules. There are no individual molecules. The bonding in a giant ionic lattice actually extend throughout the structures in all directions, three-dimensional, as I've explained earlier. So there is no limit to the number of particles present, and the numbers of particles is pretty high. As I've said, millions and billions are not the words to describe them. The structure of magnesium oxide, MgO, it has the exactly same structure as sodium chloride. The only difference is that lattice is held by stronger forces of attraction because magnesium is a positive 2 ion and oxide is a negative 2 ion. In sodium chloride, the attractions were weaker because it was in between positive 1 and negative 1 ion, which means if we're going to talk about positive 3 and negative 3 ions example, which we recently did for aluminum as a positive 3 and nitride as a negative 3 ion, for aluminum nitride, yeah, the compound has even stronger forces of attraction than both of these, magnesium oxide and sodium chloride. So the stronger forces of attraction comes from a bigger charge. Okay, the physical properties of ionic substances. Ionic compounds have high melting and boiling points because they have very strong electrostatic forces of attraction. Remember, all the properties that we are going to discuss, we are also going to discuss the reasoning. So you must be aware of all the properties as well as the reasoning. A lot of energy has to be supplied to break the strong electrostatic forces of attraction, to melt them or to boil them, hence high melting and boiling points. Now, ionic compounds tend to be crystalline. This actually reflects the regular arrangement in the lattice, the powerful microscopic alternative arrangement of positive and negative ions. Magnesium oxide is seen as a white powder because the individual crystals are too small to be seen with the naked eye. Ionic crystals tend to be brittle. This is because any small distortion in a crystal will bring the ions with the same charge alongside one another. As you can see, that the positive ions are now in front of positive ions and the negative ions are in front of negative ions. So the charges repel each other and the crystal splits itself apart. We call them brittle. Ionic substances tend to be soluble in water and they tend to be insoluble in organic solvents such as ethanol, alcohols, hydrocarbons, hexane, petrol, carbon tetrachloride, the list goes on. The reason, because ionic compounds tend to be soluble in water, is quite complicated. We cover it when we discuss water in this covalent structure. The molecule is called polar because it has a little bit of charges, not the complete charges that we get here in ionic bonding by the complete transfer of electron, but water has the capacity to track the charges. So it may dissolve ionic substances, but remember, not all ionic substances are soluble in water. Magnesium oxide is insoluble in water because the attractions between the water molecules and the ions aren't strong enough to overcome the very strong electrostatic forces of attraction between magnesium and oxide ions. Hexane is nonpolar. It does not form strong enough interactions to the ions to break apart the ionic lattice. So anything is, if it's soluble, means the solvent can break apart the forces or the ionic lattice. If it's insoluble, remember that they don't have any strong enough attractions to break apart the lattice. Lastly, the electrical conductivity of ionic substances. Now this is going to be a little bit tricky and we're going to discuss three different states for electrical conductivity. First, ionic compounds don't conduct electricity when they are solid. In solid state, this is because ions are fixed in position, they cannot freely move around, they do not conduct electricity in solid state. However, they do conduct electricity when they are molten, because then the ions are free to move, or when they are dissolved in water, aqueous solution, third state in this case, and the ions are free to move. When the ions are free to move, they carry current. When the ions are not free to move, ionic compounds become insulators and they do not conduct electricity. Molten means the salt has been melted and converted into a liquid. Liquid means free flow. Free flow means ions can flow, carry the current, and hence become good electrical conductors. So yeah, summarizing it up, in solid state do not conduct electricity. However, they do conduct electricity when molten or when dissolved in water in aqueous solution. That's about it. We finished the ionic bonding chapter. Thank you.